The Stanley steam car is a fascinating machine, and it's surprisingly uncomplicated when it's fully understood. One of my favorite quotes from George Woodberry's wonderful 1950 book, The Story of a Stanley Steamer, is this one. "My first glimpse into the vitals of a Stanley steamer appalled me by the apparent quantity and complexity. Then the situation became clarified. It was different, wildly different from a conventional automobile, and vastly simpler. Much simpler than just the electrical system alone of an internal combustion machine. And compared to today's electronically controlled engines, this difference is even more dramatic. The Stanley is basically a collection of fluid systems. The word fluid in this case includes vapors and gases, and it has very few moving parts. So this is the third of 3 presentations which explain those systems in a new and orderly way. They don't try to show the actual layout of any individual car. Instead, they are stripped-down schematics that show functionality as simply as possible. These presentations are based on the functions in a typical non-condensing Stanley in the collection at Auburn Heights where I volunteer, our 1914 Model 607. There are some slight differences in older and newer Stanleys, but the basic functionality is always the same. In this presentation, we'll be looking at the movement of both fuels of a 2-fuel car, for the main burner and the pilot burner. First, let's take a look at some of the symbols I use, because these are not industry standard pipe fitter symbols for these functions. A red line represents a tube or a pipe, and if there's significant flow of the fluid inside of it, an arrow will show the direction of the flow. These are hand valves. The black line crossing the fluid line shows that they can block the flow at that point. And this is a check valve, which allows fluid flow in only one direction. In this example, fluid can move from left to right, but it can't move from right to left. So let's start with the boiler and the burner. The boiler is described in detail in the first of these presentations on steam, so please check that out. We don't need all that detail for discussion of the fuel systems. The burner used on the Stanley is a vaporizing burner. The fuel is heated, boiled, converted to a vapor, and then mixed with air before being burned on a large circular grate that's as big as the boiler. Technically, this is referred to as premix combustion. In the Stanley design, the heat for this vaporization comes from the burner itself. The burner needs to have its fuel supplied under pressure, so we use this small tank containing fuel in the bottom and a pressurized air cushion in the top that forces it out. The air cushion needs to be pretty large to have plenty of reserve pressure available as fuel is forced out, so a second tank holds additional air. The pressure is maintained at 140 psi, and the fuel is kerosene. Kerosene is a fuel with a high energy density, and it's a little safer than more volatile fuels like gasoline if there was a leak in the system. At this point, it's worth noting that the car's fuel is not coal or wood. Their energy densities are much lower. You need a much larger volume of fuel to produce the same amount of heat. For an automotive power plant, you don't want to be pulling around a trailer full of wood. Liquid fuel is also much more easily handled. It can run through small tubes, and it doesn't have to be physically thrown in a piece at a time while you're driving. And finally, using a liquid fuel allows us much better control of the fire. In a locomotive, there's no way to turn the fire off quickly, other than to dump all of the coal onto the ground. And obviously there wouldn't be a way to get the fire relit after that happened. For the frequent and fast demand changes of automotive use, the liquid fuel permits quick shut-off of the heat and a quick restart when we need it. So we add a pressure gauge, located where the operator can see it while driving. The air here in the pressure cushion tends to be slowly absorbed by the fuel, so it needs to be replenished sometimes. There's a connection here that looks like a tire valve and allows for adding air to the tanks. So now we let the fuel out of the pressure tank and send it right across the flames of the burner to be converted to a vapor. The vapor is shot into the underside of the burner at high speed, mixing with air, and then burning above the grate. If you're thinking ahead, you might wonder how to get your first kerosene vapor in the morning when all the parts of the car are stone cold. That requires the magical bootstrapping process called firing up. Those details are outside the scope of this presentation, but we will touch on that a little bit later on. Obviously, we need to shut the fire off when the boiler reaches operating pressure. We add a hand valve to do this, the main burner valve or the main fire valve. This valve is easily accessible from the driver's position. We could simply monitor the boiler pressure gauge, which isn't shown in this picture, continually opening the main burner valve when the pressure gets low and closing it when the pressure is high enough. But having to stay this involved with managing the burner while driving became intolerable in the earliest days of steam cars, and it was realized that a pressure-activated valve could do the same job. This valve is called the steam automatic. This line carries pressure from the boiler, although nothing really moves inside of it. Now the operator can just leave the main burner valve open. When the pressure is high, it pushes against a diaphragm in the automatic here and closes a valve in the fuel line, and the fire goes out. As steam is used and the pressure drops, the diaphragm relaxes, the valve reopens, and fuel can again flow into the vaporizer. Now, we don't ever want to let the boiler run dry. If managed properly with the tools shown in the water system presentation, it will not. But an operator error could result in the boiler becoming empty. This is a bad thing because the burner is so fiercely hot that it can soften the steel of the boiler and allow it to warp under pressure, causing the ends of all of these tubes to leak. Sometimes the boiler can be fixed. More often it has become junk and has to be replaced. To guarantee that operator error won't cause this expensive ruination, the Stanleys added an automatic boiler protection device. This is the low water automatic. It's a simple thermostatic device with a tube connecting to a point in the boiler that should always be covered by water. Since the device is out in the air, uninsulated, it stays relatively cool. If water drops far enough to uncover the entrance to this tube, steam fills it and it expands and gets longer. A valve connected to its other end pushes into the fuel flow, shutting it off and stopping the danger of exposing an empty boiler to the fire. If it's set up correctly, this automatic can easily be tested before every run to make sure it will do its job properly if called on. If you look at the pressurized fuel here, you can see that it's always pushing against at least one of these valves. When the fire is out, we might need to service one or more of these valves, or we might need to do some diagnostic work. We'd like to be able to do this without all of the fuel in the pressure tank being pushed out. So we add another hand valve at this point in the line. This valve is within reach of the driver, so it could also be used to shut off the fire in an emergency if several of the other valves failed simultaneously. And that's it, the entire pressurized portion of the main fuel system and its controls. Now, obviously, the fuel in the pressure tank has to be constantly replenished while the car is running. This small amount would only feed the burner for a few minutes. So the first thing we need is a supply tank that holds a lot more fuel. This is a good time to note that the use of the small pressure tank, which is a special Stanley feature, allows us to run the car with only a small amount of fuel pressurized. If there was some kind of uncontrolled fire, only a little bit of fuel could be forced into it. The main fuel tank is not under any pressure. Well, we have to move the fuel from the supply tank to the pressure tank, so we need a pump. This is a plunger pump, not a piston pump, so the plunger doesn't make contact with the inside wall of the pump. The packing, in green here, seals the plunger's movement. When the plunger is pulled outward, it creates suction here and draws fluid in. When it's pushed back in, it creates pressure here and forces fluid out. The pump is connected directly to the engine by a long rod, so that whenever the car is in motion, the pump is moving fluid. We need a line to bring fuel to the pump, and we need these two check valves to make sure that everything moves only in the proper direction. When the pump draws fuel into itself, we don't want it to draw from the delivery line, so this outlet check will keep that from happening. And when it forces fuel out, we don't want that to be sent back to the tank. This inlet check will keep that from happening. Here's the line that carries the fuel from the pump to the pressure tank. Notice that there's now a second arrow here because fuel flows up this line when the pressure tank needs to be replenished. Now, this pump is sized to deliver more fuel than the burner needs, even at full blast. They wanted to make sure that the burner was never starved when the car was moving. So we need to do something with that extra fuel. We add a bypass line that lets extra fuel return to the tank. But we can't leave it open when we need fuel, so we need a valve here to close off the bypass and make sure fuel moves to the pressure tank when it's needed. This is the fuel automatic. There's a diaphragm inside, and the pumped fuel pushes against it. When the pressure in the line reaches our 140 psi, this valve opens and allows fuel to bypass to the tank. If we think about what's happening in a steady state when the car is moving and the fire is on, we see 140 psi here because of the tank, and here because of the fuel automatic, and the pump is delivering more fuel than we need. So what's really happening is that much of the output of the pump is going directly across here to the burner, and the rest of it is going past the fuel automatic back to the tank. The pressure tank is really only serving as a buffer to the rapid pressure oscillations caused by the pump strokes. When the pressure tank really comes into play, though, is during firing up. In this situation, the car is still, so the power pump isn't supplying any fuel to the burner. It all has to come out of the pressure tank. This only holds enough for a few minutes of fire, so there has to be a way to periodically refill it. So we add a hand pump to the system. This one doesn't draw directly from the tank. Instead, it draws from the power pump's delivery line and then pushes the fuel back into that same line. Both of the power pump's check valves act like inlet checks for this pump, so we just need one more check here to keep system pressure from pushing back on the hand pump. And finally, unless all of these checks and the fuel automatic are seating perfectly, there is a risk that when the car is not moving, the 140 psi here in the tank will push all of its fuel back into the supply tank after a while. So we add this valve, called the pressure retaining valve, to isolate the pressure tanks from the entire supply system. When you park for lunch, if you close the pressure retaining valve, you should still have your 140 psi when you come back out to drive away. And here we should look at what will happen if you forget to open the pressure retaining valve before driving away. The pump will start when the car is moving, but the fuel movement is blocked here by this valve, so the fluid pressure here quickly overcomes the fuel automatic setting, and all the fuel circulates back to the tank. The fuel in the pressure tank is slowly drained into the burner, fuel pressure drops, and steam pressure drops, and then suddenly you remember. And there you have it, the entire main fuel system. A little more complicated than water and steam, but easy to comprehend. Now, let's go back to that advantage of a liquid-fueled burner, the ability to quickly stop and restart the fire. Stopping, it's pretty obvious. One of these valves closes, and the fuel flow comes to a halt. But what happens when that valve opens again? Fuel starts flowing, it gets vaporized and shot into the burner, but something has to light that big burner again. So we use a little burner, just a tube about 6 inches long. It's called the pilot burner, and it burns continuously when the car is in use. Here it's shown separately, but it's actually located inside the main burner. When fuel vapor starts coming into the main burner again, the flame of this little burner lights it off. It's a vaporizing burner too, so it needs pressurized fuel, but in this case the fuel is much more volatile, usually a solvent named hexane, and the fire is small, so the supply pressure doesn't need to be as high, usually around 25 psi. So, in this case, with a small quantity and low pressure, it's okay to pressurize the entire supply. Of course, we need to monitor this pressure, so there's a gauge, and there's a way to add air if the pressure gets low. Same idea as with the pressure tanks up here. And it has its own little vaporizer, and the vapor shoots into this little burner, just like it does for the big one. And of course, we need a valve to shut off the pilot when we put the car away. And that's it. The pilot is a very simple, independent system. We don't need many controls because it doesn't have to respond to rapidly changing conditions like the main burner does. But there is one interaction between the pilot system and the main burner system. As part of the firing up bootstrapping process mentioned earlier, we make use of the easily vaporized pilot fuel in one of the early stages of getting the main vaporizer hot enough to vaporize kerosene. We add a line to allow the pilot fuel to enter the main fuel system. And this is another great place for a check valve, because we don't want an accidental opening of the main burner valve to let this 140 psi push kerosene into the lightly pressurized pilot tank. And of course, we need a valve to control this temporary pilot fuel feed, the firing up valve. And there you have it, the entire schematic diagram of the main and pilot fuel systems. Note that of all of these parts, the driver doesn't need to work any of them during normal operation on the road. Manual controls are only needed during starting and recovery conditions. This diagram is available for download at the link below. Hope you enjoyed the presentation. Be sure to check out the first one, steam and cylinder oil, and the second one, water, if you missed them.